Good morning to everyone. Today I will present our work titled Investigation on a Realistic Stack-on of Defects to complement the IEEE P2427 draft standard. My name is Nicola Dall'Ora. Currently, I am a third-year PhD student at the University of Verona. The focus of my PhD is the multi-domain simulation and abstraction of cyber-physical systems. Moreover, I am analyzing how different classes of defects injected in analog circuits produce behavior alterations inside the cyber-physical systems. I am currently part of the Cyber Physical and IoT System Design Group inside the University of Verona. The focus of the proposed work is on transistor-level defects, but what are analog defects in the reality? We need to distinguish between fault and defect, as suggested from the literature. In the context of transistor-level netlist, a fault is considered to be an unexpected change in the performance of a circuit, whereas a defect is an unexpected modification of a physical structure, likely to impact to the function of a subsystem and cause a faulty behavior, a failure mode, or equivalently a fault. The image present on the left show a possible location of a defect into a transistor level schematic, and on the right the physical modifications of the same defect in the reality is presented. The figure is taken from the IEEE P2427 workgroup web page. As stated into the IEEE P2427 draft standard that categorize the defect for a MOS inside a transistor level descriptions, explain that the most common defects are short and open, but there is nothing about stack on and off that are not covered by a standard short and open. When we speak about short and open inside a MOS transistor, we refer, for example, as shown in this slide, for example, to a short between drain and source, or for example, an open on the source of our MOSFET. While historically the concept of stack-on-off defect did not originate from physical observations, but rather to model the behavior of faults at the gate level and not at the physical level. Digital stackette fault model, where a transistor is considered frozen in on state or off state, may not apply well on analog circuits, because even a slight variation could create deviations of several magnitudes, and this is our case, because into an analog circuit we could not refer to stack on and off as mentioned for the digital part. We cannot consider a stack on like a digital stackette 1 or stackette 0, but we need to consider the physical behavior that a stack on or off produce on the physical circuit. This is the main motivation for this work. We had proposed with this work, we propose two new defect models to model stack-on and a stack-on, but with a physical behavior. But how to model a stack-on or stack-off that have a physical behavior and not a digital behavior? We had start our research by looking in the work of Esqueda and all, that had proposed a study in which he studied the physical behavior of a defect inside a transistor level netlist. And our proposed work starts from the SCADA work and propose a new stack-on of defect model implemented as transistor level netlists and based on the concept of excess of trapped charge in the oxide and excess of interface traps into our MOS. Our present investigation is driven by the intuition that none of the hard defects as envisioned by the IEEE P2427 draft standards seems to naturally cover the transistor stack-on or stack-off behavior, which are known to occur in a MOSFET and are caused by excess or trapped charge in the gate oxide or excess of interface states. And this is related to the work of SCADA. In this slide, in the top left, is showed the cross-section for a MOSFET, and in which trapped charges are marked in red with an O, are fixed positive charges which are trapped in the gate oxide and have as primary effect to shift the threshold voltage, while interface traps represented in the image in the cross-section of the MOSFET with a red X are parasitic states which can capture and release minority carriers normally intended to populate the channel but which get blocked in the trap and get not participate to the current conduction in the channel anymore. Traps reduce the efficiency of the MOS gate to attract carriers into the channel for conduction. They manifest themselves as a reduction of the sub-threshold slope and a shift of the threshold voltage. And by following the research made by SCADA, we had built two new two new defects for a stack-on and a stack-off. In the bottom left, it is showed the transistor level description of our stack-on defect, in which we have two transistors, Phi0 and Phi1, and a voltage source. The fault is active. The changing in the behavior of the MOS is guided by changing the multiplying parameter inside the netlist, and we switch from the Phi0, that is the transistor fault free, to the Phi1, that is the transistor faulty, during a slower time. And this allows to model the stack-on behavior relative to the oxide trapped charge, while to model the interface traps inside the substrate, we had modeled a more complex schematic that is composed by a transistor fault-free and 4 additional transistors for the faulty case. In this slide are shown the results for a PMOS and an NMOS regarding different behavior generated by different defect models. And MOS hard off was related to a defect where the gate is forced in the off state by disconnecting the gate terminal and forcing it to follow the potential of the body, while MOS hard on is related to a defect where the gate is forced in the on state by disconnecting the gate terminal and forcing it at a sizable potential difference above the body terminal. These two naive defect model are related to what the IEEE P2427 draft standard mention for stack at false, while in this graph the behavior of the most stack off and most stack on are related to our proposed new defect model. In this case, the defect for XX fixed oxide charges is labeled as most stack on, as this is the behavior which most closely approximates the effect of those charges. The defect corresponding to XX interface charges is labeled as most stack off, as the current in this case is substantially lower than that of the fault-free case. The first model used to compute the results and to test the methodology is a comparator circuit retrieved from the analog benchmark circuit suite available from the IEEE P2427 working group website. The faults considered in this article are all the variants of open and short circuits for each MOS inside the design. The second circuit used to compute the results and to test the proposed stack on and off defects is an operational amplifier circuit retrieved from the analog benchmark circuit suite. The first fault grouping technique presented is the waveform-based grouping. This grouping method allows to group in clusters faults with the same transient behavior. This means that different groups of faults are generated by computed distance between the waveforms. The plots are related to the op-amp circuit. On the left, all the waveforms for the injected defects are shown, and on the right are shown two different groups for all the faults on the right, obtained through the waveform-based grouping. Obviously, these two different groups are not only two, but the optimal number of groups for this particular model are 15, and two faults are equivalent with this method when the waveforms are the same in all the conditions. To move from the waveform-based grouping to the AC-based grouping, it's necessary to know the concept of operating points. The graph on the right shows a transient behavior obtained through a transient simulation in blue. Then, at specific operating points, the faults FA and FB are injected. It is important to sample all the important states that are the regions where the linearized model is applied, the green arrows. In our approach at specific operating points, we analyze the circuit with the frequency analysis, and consequently to it, the proposed AC-based grouping method remains valid even when the environment changes, because it is based on the AC matrices. Based on the data extracted through the frequency simulation running at precise operating points, it is possible to extract the matrices necessary to apply the AC-based grouping. These AC matrices extracted in our case are S-parameter matrices that are composed by complex values. The equation shows the metric used to subdivide the faults in clusters, and it is based on the root square of the distance between each pair of S-parameter values. This fault grouping is more general respect to the waveform-based grouping, because its valid for any loads are load independent. By analyzing the frequency response, we are able to catch more behaviors and compare it to subdivide the faults in clusters. In these slides are shown the results of the grouping for the op-amp circuit. The two plots are dendrograms, and on the left are shown the results for the waveform-based grouping, while on the right are shown the results related to the AC-based grouping. In both of the plots, the defects are subdivided in 15 clusters, the optimal set for this model, and the results are equivalent, but the time spent to obtain these results is different. To compute the results for the with the waveform-based grouping, is necessary a lot of time to simulate all the defects with a transient analysis, while to obtain the same results with the AC-based grouping, a small fraction of that time is necessary. The final results are reported in these two plots. The plots show the comparison between IEEE P2427 defect and the two proposed defects, named stack on and off. On the left are present the results for the op-amp circuit, while on the right the results for the comp circuit are shown. These plots are related to the result of the AC-based grouping. In the plots matching close to 100%, color yellow means that the fault type on the row was in the same group as the fault type on the column, nearly all the time for all the instances in which it was injected in the reference circuit. For the comp circuit, it looks like for some faults there are more than one fault candidate that is equivalent respect to the results for the op-amp, and it is easy to see how standard defects defined in the IEEE P2427 draft standard cannot produce the same transient behaviors generated by the proposed stack on-off defects. Now it's time for conclusions. In this article we have analyzed the behaviors of the defects proposed in the IEEE P2427 draft standard for a MOS component, and two new defects are proposed to complement the standard. These two defects proposed are named stack on and off. Our analysis showed that in hard defects there are no correlation with the physical defects proposed. Physical stack on-off proposed generate a new failure mode that it is necessary to take in account. Moreover, different fault grouping techniques are proposed to group the faults with equivalent behaviors in clusters, to reduce the set of faults to simulate, to calculate the coverage matrix. As future works, we plan to apply the proposed defects on more complex design, respect to the design proposed in the analog benchmark suite, and improve the techniques to obtain an optimal set of faults to simulate. Thank you for your attention. If you have questions or you want to collaborate with us, you could contact me, Nicola Dall'Ora, from the University of Verona, or Renaud Gillon from the Fidelity Company, Belgium, that collaborate with us. Thank you again.